Hello everyone, and welcome to part 1 of our chapter 16, which is acids and bases. In this chapter we're going to look at the different definitions of acids and bases through the years. We're going to look at the relationships between an acid and a conjugate base and a base and a conjugate acid. We're also going to look at properties of solutions of acids and bases. We're going to learn to balance acid-base reactions, look at strong electrolytes, and look at their ion concentrations, as well as the auto-ionization of water, understand the pH and pOH scales, and then use ionization constants to look at weak monoprotic acids and bases. So in this first part, we're going to look at Bronsted-Lowry acids and bases and their conjugates. So general properties of acids: they're sour taste, they will dissolve most metals, they neutralize bases, and then they change blue litmus paper to red. And one you're probably familiar with is acetic acid, which is vinegar, which we do consume. And this is just a list of common acids and bases, or common acids and their uses, and so you can look over that. We do use acids a lot in food and beverage and manufacturing. An organic acid is called a carboxylic acid, and these are typically weak acids. These organic acids have this COOH group. The COOH group is at the end, and so when we generally, with our inorganic acids, have written the H at the beginning of the equation, but often you'll see it just mixed in with the equation on these, and so if they're being kind to you, they'll add it at the beginning, but sometimes they'll just have the COOH at the end of the acid, and so that's just how you recognize those carboxylic acids with that COOH group or alkyl group. So bases taste bitter. Okay, bases taste bitter, and the other word for basic is alkaline. Okay, so alkaline also means on the basic side. Usually in nature, alkaloids are poisonous, and so they have that bitter taste to warn animals not to eat them because they're poisonous. They're slippery. If you get them on your skin, you might think you've got it washed off, but you probably don't. It takes a while to get it off. It will neutralize acids, and then it changes red litmus paper to blue. And so typically these are a lot of our cleaners, like ammonia, for example, bicarbonates, and then your sodium hydroxides and things like that. So in an acid, you have something called a hydronium ion. Now you're going to see us use an H plus equal this hydronium ion, because depending on how you're putting it in the reaction, it just makes it easier to balance if you have an H plus in there sometimes. So that's why you'll see them used interchangeably, the H3O plus and the H plus. But where this hydronium ion comes from is that you have the H plus added to your water, and then that forms H3O plus. And so that's where the hydronium ion comes into play. When you're acidifying the water, then that hydrogen adds to the water molecule and forms the hydronium ion. So we've had several definitions of acids and bases through the centuries. The simplest and most restrictive is Arrhenius. Okay, the Arrhenius definition says that acids, when dissolved in water, will produce a hydronium ion. Bases will produce a hydroxide ion. Now, that was great at the beginning, but we found as we moved forward in chemistry that did not cover all the instances. And so the Bronsted-Lowry definition was based on the reactions in water, said that acids still donate protons, okay, the H plus. but bases accept protons, the H+. So if you're looking to see if it's an acid, you see if it has a hydrogen that it could donate or give away. And then if it's a base, can it accept a hydrogen? Okay, and so we're going to look at some examples of that in a minute, because this is the primary one we're going to use. Okay, Lewis definition is based on electron donors and acceptors. So instead of looking at it from the proton side, Lewis acids and bases are defined by the electrons. And so acids in a Lewis are a substance that can accept an electron pair. Bases are, as you might guess, something that donates an electron pair to something else. So Arrhenius, we said it has to be one of the bases that has the OH in it in order for the Arrhenius definition to work. Okay, and so if you've got hydrochloric acid, you've got H plus and Cl minus when you put them in water. Okay. In the sodium hydroxide, it breaks apart or hydrolyzes into sodium and hydroxide. And so if you have an H plus and an OH minus made up of water, then when you add those two together, it forms water. So when you add an acid and a base, you're going to form water, and then you're going to form a salt. And the salt is made up of whatever the anion from the acid is and the cation from the base. So if I have, here's my H and my OH, all right, and they're going to link up and form water. And then I'll have sodium and chloride left over, and they're going to link up to form the salt. And remember, you always write the positive one first in a formula, so that's why it's in NaCl, sodium chloride. So as I said, there are problems with the Arrhenius theory. It doesn't explain why some ionic compounds like carbonates and ammonia don't have a hydroxide present. And so that's why we came up with the Bronsted-Lowry, okay, which also can cover things that aren't necessarily those two definitions. And so all acid-base reactions that fit Arrhenius will also fit Bronsted-Lowry, but Bronsted-Lowry will have some in addition to that that don't necessarily have that OH. They're both exactly the same for the acids. They have to have this hydrogen to be able to donate it to something else. But the base is typically whatever is accepting that hydrogen from the acid in the reaction. Okay, and so when we look at this, we've got an acid, and this is the H it's donating, and the A is whatever its anion is, plus the base is going to give us the acid less the hydrogen, which is now going to be a negative charge because it lost its H plus, and a conjugate base we call it, which is the hydrogen that's added to whatever your base was starting out. And so the acid forms the conjugate base, and the base forms a conjugate acid. So so if you if it's a reversible reaction, obviously it could go either way. So it is reversible if it's doing this. If it's a weak acid, for sure. Okay. Now sometimes your strong acids and bases, when they combine, they will not be reversible. So each reactant and product is called the conjugate pair. So, and it has to be, you know, like, so if you start with ammonia as a reactant, if you add a hydrogen to that instead of having 3, it's now going to have 4. It also is going to now be plus. It's no longer neutral because this was a neutral molecule. So this one's going to be a +1 because it added that H plus to it. Your water can either be an acid or a base. It just depends on what you're adding it to. If you're adding a base to it, it's going to act as an acid. If you're adding an acid to water, it's going to act as a base. Because remember, water is neutral, and water is where all of these things are happening. And so in this particular case, if you're adding a base to the water is going to act as an acid, and it's going to form a conjugate base because the OH minus is HOH, what? Minus the H plus, which is going to leave you the OH minus. So when you look at the reaction, you're going to have, you first identify what, especially if it's like plus water, identify what the other one is, okay? Ammonia is a base, all right? It's on the base list, all right? It's a weak base, okay? So over here, something's going to look like NH3, all right? It's NH4. So those two things are going to go together. What happened to that was you added an H plus to it, which means it accepted a hydrogen or a proton, which made this a base and this a conjugate acid. Now, why is it a conjugate acid? Because if this is reversible, then it could lose this H plus again and reform the NH3. So it could give up its extra hydrogen, which would then make it a proton donor. Okay, so a base will accept a proton and become a conjugate acid, and an acid will donate a proton and become a conjugate base. We know that water must be the acid because if one is an acid, the other has to be a base, right? So the acid becomes the conjugate base. All right, so we can look at these and we just need to decide which is the acid, which is the conjugate base, which is the conjugate acid, which is the conjugate base. All right, so when I'm looking over here, I've got H2SO4 plus water. Notice that it's got one arrow because it's going to go to completion, SO4 minus and H3O plus, because this is a strong acid, okay? And that strong acid is going to completely ionize. What happened to H2SO4? It turned into HSO4 minus, which means it lost a hydrogen. So it gave up a hydrogen, so it must have been an acid. If that's the acid, this is the conjugate base. If the sulfuric is an acid and it's reacting with water, water is acting as a base in this reaction, and the base accepted that proton, okay, and became H3O plus, so that is now a conjugate acid. See how that works? HCO3 minus plus water is reversible. H2CO3 plus OH minus. So in this case, the HCO3 is going to do what? It's going to gain, right? Because it's gaining here. So this is conjugate acid. This was the base. So that must be the acid. And that must be the base. And you could figure that out easily because OH minus is obviously going to be a base, right? So easy as that. You just identify which one is going to be the acid base, conjugate acid. Okay? All right, and these are according to Bronsted-Lowry. All right, and so there's a practice for you. So if you want to stop and work that now, you can, or you can wait and do it later. I want to mention acid strength and molecular structure of acids as well. Binary acids means that you have a hydrogen and then a single thing attached to it. And so, and they're going to be nonmetals. And a lot of them are your halogens, your chlorine, fluorine, bromine, iodine. HCl and HF are binary acids. The more polarized the bond, the more acidic. Okay, the stronger the bond, the weaker the acid. The strongest bond is this one right here, and that is a weak acid. All the rest of those are strong. So your acid strength increases as you go across the periodic table, left to right, and down the down the column, down the group. And that is it for the first part of acids and bases.